Hello there Chem fans, welcome to my channel on chemistry lessons. This is AQA A-level chemistry and it's an introduction to NMR. So this is what the spec says and these are the sections that this video is going to focus on. First up though, if you don't subscribe, please do. Your support is very much appreciated. Thank you. Okay, so as we said, these are the sections we're going to focus on. First up, I want to kind of bring your attention to Table B and Table C in your data book. So you do have this to refer to, and you will have to use this in the exam when you're using or completing NMR questions. So let's start here. We've already studied mass spectrometry and infrared spectrometry in first year. Infrared was used to identify bonds that were present, and the mass spectrometry allowed us to identify the relative mass of the molecule, and we could also get fragmentation patterns or the molecular mass of specific fragments if we used electron impact. We're going to look at NMR now, which is nuclear magnetic resonance. But before we do, let's have an appreciation for those scientists. I don't know how else to appreciate it. I'm just going to appreciate it. Big up to the scientists. Well done. Thank you very much. We love this. There we go. We've appreciated the scientists. So, NMR gives us information about the position of any carbons or protons in a molecule, which is obviously quite handy when it comes to organic analysis, because organic molecules contain lots of carbons and hydrogens. And if we know the environments or positions they are in, that gives us information about the molecule. This following information is not needed. You will not be examined on this, but it definitely helps our understanding. So NMR is only possible if the nucleus has an unpaired nucleon. By nucleon, I just mean the particles in the nucleus, protons or neutrons. In other words, the mass number has to be odd, hence carbon 13 and not carbon 12, because carbon 12 doesn't have an unpaired nucleon, okay? Because it has to be unpaired in order to be this kind of spin. It means it has an overall spin, because if it has an even number of nucleons, they pair up and have no overall spin. But if you've got an odd nucleon, it will have a spin, okay? That means they can act as a mini magnet. So nucleons or nuclei with unpaired nucleons can act as a mini magnet. And that's not just for 1H or carbon 13, it's true for any nuclei, but we're just doing this as organic. Now, if you apply a strong magnetic field to the nuclei will align themselves up within this magnetic field. And there's two possibilities. They can either line up with the magnetic field or against the magnetic field. So what I mean by this is, if we apply a magnetic field in this direction, then the nucleon will either pair up with it as like a mini magnet, or it will pair up, align against it, okay? Now the first one with it is known as low energy, and the one against it is known as high energy. And what we do is we apply radio waves to the sample, and the radio waves provide enough energy for these nucleons to flip between the two states, okay? And what it does is it goes to the high energy state, and then when it relaxes back to the low energy state, that energy is measured, okay? And this energy is compared against a database and goes, ooh, it was that much energy, it must be in this position, and therefore this kind of environment and these other atoms are around it. It'll make more sense as we go through it. But as I've said, you do not need to know the chemistry of that section there. Okay, so let's have a look at this then, the idea of how we measure or what this chemical shift is all about. So the energy required to flip that spin is measured and recorded as a chemical shift. And the chemical shift, it's measured in parts per million, ppm. And a high chemical shift usually indicates that the nucleus is near an electronegative or an electron withdrawing group. They're all measured, so all chemical shifts are measured against a standard or a relative. And in this case, in the case of NMR, our relative signal is the TMS signal, which is tetramethylsilane. It's 4 methyl groups on a silicon. So tetramethylsilane, that's the standard, and we give that the chemical shift of 0. Now the reason TMS is useful is because it only produces one clear signal, so that's good. And it only appears at the chemical shift away from all the other expected chemical shifts within organic molecules, so it doesn't interfere with the sample. It's also inert, so it doesn't react with our sample. And it's also very volatile, which means it can be easily removed from the sample afterwards. And that's the brief intro into NMR. What we're going to move on to next is looking at what an NMR actually looks like and how we can interpret them. Good luck. Thanks for watching.